and expanded, so they took up the space of their container. And what's the word you're looking for? Condensed. Okay, so they quickly condensed, and so did the can. But why was it the can also do that? Okay. So here anything about pressure too, Marcus?
Since you put it over the water, it created a vacuum because the gas losing its volume, and that caused overpressure.
So it wouldn't necessarily be a vacuum, because the vacuum means there's nothing in there, because there's still gas particles in there. But the whole of the can was covered. So in terms of the pressure differences from the inside of the can and the outside of the can, who had more pressure? Inside the can or outside the can? Outside, meaning the pressure that's around us right now, right? So what did it technically do to the can? Demolished it, right? It crushed it, such to the point where the pressure on the inside could not equilibrate with the pressure on the outside. Okay, so that was actually something I wanted to do yesterday. I totally forgot. We just did it. We're like, all right, going back to the simulation. But this is what's happening. Okay, so in terms of the volume, I thought it was really cool. The volume it takes up when it's a gas versus a liquid is actually 12,000 times the volume, which is really kind of cool. And that's why it's starting to come out of the top of the can. And when you submerge it, the gas instantly cools. So a lot of you guys, thank you, Jillian, got that part right there. But as the atmospheric pressure on the outside is trying to equilibrate with what's on the inside, we couldn't, because there was no transfer. The hole was covered. We couldn't actually touch the pressure on the outside. So the pressure on the outside crushed the can. There we go. Right. So I'm going to show you another demonstration that also you should be able to explain. Okie dokie. So who's off to her birthday? Ricky, when's your birthday?
That was Friday.
Friday. Oh gosh, the pressure's on. No pun intended. Okay. So, happy birthday. Okay. And come here, Drew. I don't have a lighter, so I need a human lighter. Come on this side. You're gonna get away. All right. So we have to put the alcohol away because it's flammable. I just put all my stash. Andrew, grab some glasses. Can you, just throw them to us, man. Just throw them. Good. So, can you please light this for me, sir? And so what I'm going to do, happy birthday, I'm going to hold this upside down, and I'm not going to push the egg in. Okay, I'm just going to hold it there at the barrier, and I want you guys to tell me what's going to happen. I don't have a glass of water with me. All right, so, let's go in. It's fighting me, guys. I'm sorry. Usually it pops up. Sorry, for the dramatic effect. So what happened? What happened? So it consumed the oxygen inside of it through combustion, and then what?
Then it gets pulled up because of pressure and stuff.
It gets pulled up?
Like the pressure, which gets pushed up because the outside pressure passes off.
Good. So the inside pressure was low, outside pressure was high. It pushed it in. It did not pull it in. And now, some people like to say the egg was sucked in. No, science is not suck. Okay, science pushes. All right. So one more cotton ball. Where'd the cotton ball go? There's a random cotton ball on the desk, guys. There it is. Okay. So don't you light me on fire yet, Drew. All right. So egg number 2. Un minuto. Alright, so this is a substance that is flammable. This cotton ball is humongo. Well, I'm not going to cry over spilled milk. It's cool. This is not milk. This is isopropyl alcohol. And this egg does not fit in this thing, right? Does not go. But wait. Okay. Light this on fire for me. Oh, where's the egg? Same thing, right? But what happened to the egg this time? Was it sucked in? No, science doesn't suck. The air atmospheric pressure pushed in to the egg. Thank you. Woo! All right, so who wants eggs? Brought eggs for the toast today. How do I get it out? How should I get it out, guys?
Oh, just
Burn it. How do I do the opposite? I could do the opposite. I've done it before.
Oh, I thought you would like lighting fire coffee.
I hold it over a Bunsen burner like this. I just take a Bunsen burner and I heat it and it poops the egg out. Okay, I could do that. I got that kind of time. Or what you supposedly can do, and I did my first year teaching it, we'll never do this again, but you're supposed to blow into the flask to increase the air pressure, and then it pops the egg out. So, there's pictures of that. It's not a good thing. Okay, so we're going to start here. You guys have your notes out. That looks like this. I'm going to move kind of quickly to the conceptual side so we can do the math together. Notice for homework, you guys have a problem set. The problem set we'll probably get to in 45 minutes and hopefully get most of it done in class. Okay? So I'm videoing too if you need anything to listen to afterwards. In terms of what we try to utilize for pressure, we have a couple of different measurement tools. What's the most common one that we can measure pressure with? Barometer. That's probably what you've heard of, like in earth science. A barometer is actually made of the liquid inside is mercury, so that's what this over here is. And we have a beaker with the mercury here, and the mercury that is suspended in this is called a eudiometer. A eudiometer kind of is actually what we'll use in our lab on Friday, but it's an upside down, big, huge test tube. And there's little measurements on it. And those measurements, can you guess what their measurements are in millimeters? Because we're measuring technically millimeters of mercury. So this is what a barometer looks like. We don't generally use this in the classroom because it's mercury, and mercury is toxic. So another way that we can measure pressure is using manometers, or manometers, if you want to get fancy. But it's actually the same system where you have mercury or some sort of fluid in your U, which is the arm here, here, and here. And we allow for pressure differences to move the mercury. So it's called fluid dynamics because the fluid is moving dynamically. But there's a pressure point that's caused by the gas inside of this little glass container. So I'll put P gas there. And then there's another pressure point that's actually come from the atmosphere, which is on the outside of this little U tube right here. So notice I only put P of atmosphere on the two over here because we have an open system, whereas over here we have a closed system. So we don't generically, we don't always use these because there's technically no atmospheric pressure coming into contact with the gas pressure, and it doesn't necessarily allow us to measure differences in pressure. So I'm going to go with this example first. So let's say we have mercury in here, and the mercury between pressure of gas over here, which is pushing on the mercury, and the pressure of the atmosphere, which is pushing on the mercury. So both pressure points are pushing on the mercury, but notice the mercury levels are the same. What can you then assume about the pressure of the gas? So the pressure of the gas is equivalent to pressure of atmosphere. And if we are at sea level, what would that pressure be? 1 atmosphere, or 760 millimeters of mercury, or 101.325, but I never use the 25, it's 101.3 kilopascals. One more. This guy named Torricelli, 760 torr. So Torricelli is the guy who came up with some of this stuff and like the barometer, so he named it, after himself, like all great scientists. Okay, so assuming that the pressure of the atmosphere is at sea level, we would say this is equivalent to the P gas, which is in our case 1 atmosphere. So what would be different if the pressure of the atmosphere was greater than the pressure of the gas? How would this look? So if the pressure of the atmosphere was was greater than the gas, it would be closer to the gas. So I'm going to kind of go like this. Something like that. Would that work? So notice that the pressure of the atmosphere is really doing some damage here, and it's pressing down on the mercury, pushing up on the left.
Recycling bins outside the door. Thank you.
I'll do that in a second. Okay, so it's pressing down, and so the pressure of the gas can't fight it, so the mercury level is increasing. So what we would have to do is say, okay, well, how do I figure out the pressure of the gas numerically? So you're going to take P of gas is equal to P of atmosphere, and I'm going to decide that I need to add or subtract the height difference, because remember, this is in mercury, right? Or this red stuff I've drawn here is mercury. And if I hold a ruler up to it in millimeters, I technically have what? Millimeters of mercury, which is a pressure unit, so I can use that. So this change right here is I'm going to call H, delta H, which is change in height. So that difference there should tell me the difference in height should tell me the difference in pressure. So do I want to add or subtract from the pressure of the atmosphere to get the pressure of the gas? You say that questionably. Subtract, because the gas is less than the pressure of the atmosphere. So I should be subtracting the height difference to then ensure that the pressure of the gas is less than the pressure of the atmosphere. So then vice versa, if I had this situation, what would I then do to find the pressure of the gas? So I would have P gas equals what? P gas is equal to P atmosphere plus, and the delta H, and I don't know if you saw me, but it's the point at which the height is at its extreme, and then where the other arm is in terms of level. So this difference right here is called delta H. So I'm going to add delta H to the P of atmosphere. So just that's getting you comfortable with reading manometers or barometers, and a lot of times though we just have the pressure given to us. So occasionally you have to do that. So we know our measuring units. We know that all of these are equivalent, so we can convert between the units if we needed to. And check, we got this. Those are all standard pressures. What is standard temperature? I heard it to 73 Kelvin, which is what in Celsius? 0 degrees Celsius. Okay. And yeah, let's go. All right. Oh, this is another situation with the barometer. So, in terms of how does this atmospheric pressure kind of play into this, you've got the same situation. The mercury's on the bottom. The atmospheric pressure is pushing down on the mercury, but where's that mercury going once it's pressed? Up the tube. So that's going to increase as the pressure of the atmosphere gets greater. It's going to continue to press the mercury up, which is why we have 760 millimeters of mercury, but as you go up, the pressure gets higher. So in a situation like this, I'm going to go back down to this question here. If instead of having 760 millimeters of mercury, instead I only have 750 millimeters of mercury, where would I be? Would I be above sea level or below sea level? Okay, so here's a mountain. Here's us with our goggles on, okay? And then here, we're swimming, flippers, arms. We're just chilling, okay? So this right here is 760 millimeters of mercury. This is sea level. As you go down beneath the ocean, you've got all of this atmosphere pushing down, plus the extra, right? Plus this water pressure. So as you go beneath the ocean, what should your pressure do? So like, I don't know, 800, something like that, 800 millimeters of mercury. And as you go up on a mountain, you have less pressure pushing down on you. So what should your atmospheric pressure now be? So decrease, I'll say like 720. That might be detrimental to your health, but there you go. So you should be able to consider that from like a landscape perspective. So this one is what? Above or below sea level? Above sea level, okay? And if I had to convert 750 mils of mercury to atmospheres, let's just make sure we can convert that right now. 750 mils of mercury to atmospheres. What's your conversion factor? So 760 millimeters of mercury is equivalent to 1 atmosphere. So let's just guess and then calculate. Point what? 0.9 and some change. What is it in terms of actual calculation? 9 what? 86 atmospheres. Okay, I may not have rounded correct fixes. I mean, I was listening, but I wasn't listening. Okay. And over here, one thing I wanted to mention about mercury is, now we use mercury in barometers because it has a very unique property. It's its density. What do we know about the density of mercury? Is it super dense or super not dense? Super dense, right? It's very, very dense. So what do you know about the particles? Very, very close together, right? Okay, so I can put mercury in this very confined space, and I can still get a lot of matter in one place, which makes it actually measurable. If I had to measure something like this with like water, the pressure that the water doesn't respond to pressure as well as mercury does. So we'd have to have a huge column of water to actually measure the pressures, where in mercury we can have a reasonable sized column to measure that. So that's why we use that. The density of mercury is 13.6 grams per milliliter. What's the density of water generically? 1. So this is density of mercury. Mercury. And this is density of water. So it's quite different. That's why we use mercury. You guys good? Okay. So I think we went through enough of this. You guys good on here? Measuring height differences, adding, subtracting as needed. Thumbs up, please. Okay. All right, so here's your scenario. You've got an open manometer filled with mercury and connected to a container of hydrogen. So how does that look? What's the manometer look like? Circle thing. What's in here? Which gas? Hydrogen. Okay. It's connected to this little U-tube. Open end over here. And what's inside of this? Mercury. Okay, I don't know how much, we'll see in a second. Heat of the atmosphere is on the outside. It's pushing down here. Okay. The mercury level is 78 millimeters higher in the open arm. So now how does this look? Like this or like this? Do it according to you. The right side's high, okay? So we have mercury, all the way up here. And so this height difference from here to here is what? 78.0 millimeters of mercury. The air pressure, so when it speaks of air pressure, what is it referring to? P of atmosphere, not P of hydrogen gas. So P of atmosphere is 100.7 kPa. What is the pressure of the hydrogen gas in kilopascals and then separately in atmospheres? Go. I'm going to be talking a little bit longer than normal today. I know, it's bad. When you need a break, let me know. We'll do like a class break. Alright, check yourself here. I just embedded my work, so I didn't do a separate calculation, but KPAs, 111, close to that. Notice, and the reason we're doing this is because we cannot add KPAs to millimeters of mercury. We can't just simply add those because they're two different units. So we must show the conversion from millimeters of mercury, which was the height, to kPa. So I've taken this, used this conversion factor of 101.3 kPa divided by 760, which is the equivalence of 1. So I'm not truly changing anything but the units. And as I add that now, it should be close to 111. And then you could have done the atmosphere one first and then vice versa, done kPa, but from your kPa, relationship between kPa and atmosphere is 101.3 to 1 atmosphere, multiply 1.1. Yes, ma'am.
Can you summarize why did you ask?
Yeah, so when I look up here, and this is just the most logical way I can think about it, I first tell myself, okay, the mercury has moved towards pressure of atmosphere, so gas must be stronger. Gas must have more pressure. So if I'm going to make the pressure of the gas higher than that of the atmosphere, I must add the pressure of atmosphere and the height to make this a larger pressure. That's the most reasonable, like the logical way to do it. Questions here, guys?
Will the pressure of the gas always be like 1 atmosphere?
No.
So like if they're equal, it doesn't necessarily mean if it's at 1.
Oh, so if I say that they're equal, meaning the arms of the mercury level is equal, and I'm assuming that most of the time we're dealing with sea level, then yes, it would be 1 atmosphere. But I could also say, hey, the atmospheric pressure is, 1,000 kPa, and then when it's equal, then you'd also say the gas pressure is 1,000 kPa. So if the scenario is given to you differently, then go with what's given. All right, so that's how you deal with drawing the manometers and going from there. Now we're going to go back to the stuff that you guys were mainly dealing with yesterday, which was relationships between pressure, volume, temperature, moles, and some of the gas laws probably are coming back to you. Who feels like they have a strong memory from honors chem of gas laws? Like pretty strong. So if I said Boyle's law, anybody? B1 equals P2 V2. Anybody say Charles's law? V over T. So because Charles went to Virginia Tech, VT. He didn't, but that's what I tell you. Ideal gas law? PV equals nRT. So some of these things might be coming back to you, but they should be very strong after this, okay? So I'm trying not to assume too much because I know we had different experiences. All right, so Boyle's law, you don't necessarily have to know the person and then the law or the variables that he designed or he or she designed, but it's nice to kind of put it back in context like you learned in honors chem. So Boyle's law is a relationship between pressure and anybody? Volume. Okay, I don't know. I didn't tell you to bring this today, but whip out your box of air. Whip it out. Box of air. Okay, you have a box of air. It has yay volume. Increase your pressure. Let me see you increase your pressure. Okay, so you increase your pressure, what happens to your volume? It decreased. So is that a direct or an indirect relationship? Say again? So as pressure increased, volume decreased. So indirect. Okay, so this is indirectly proportional. All right, so the equation that we will generally use is going to be P1V1 equals P2V2, and this is going to be at constant what? Temperature and number of moles, or as it was stated in your simulation yesterday, amount. So the idea is that if I give you scenario 1 where you're at sea level and you have a balloon, okay, your little balloon, yay big, and if you travel up to the top of Mount McKinley, you know where that is? Where's Alaska? It's in Alaska, yes. So as you travel up to the top of Mount McKinley, what happens to the pressure? It goes down. What should happen to your volume? It should increase. So the idea is that you go from scenario 1 to scenario 2 in your head, like qualitatively, but mathematically using this equation, P1V1 equals P2V2. The appropriate units for pressure here could be any of them. Millimeters mercury, atmospheres, kPa, torr. The appropriate unit for volume could be either what or what? Liters or milliliters likely. Otherwise, as long as they're the same unit from 1s to 2s, you're going to be fine to cancel those out. So what the idea is that Boyle kind of came up with was, he said this was a very predictable pattern, but it's most predictable and it's most linear in terms of the relationship, or I guess indirect. He graphed volume versus 1 over P to make it a straight line, but it's still relationship indirect by the nature of flipping the P variable. He said that this is only true at low pressures, and that's because particles under low pressures are close together or spread out. Let's get more people involved. Low pressures, gas particles are close together or spread out? Spread out, okay? So they're spread out a lot, and as you increase the pressure, what happens to them? They get close together, right? Well, you may not remember this, but as some things get close together, they start to interact. As molecules get close together, they start to interact. What is that term called? Say again? intermolecular forces. Okay, so some of those examples were like hydrogen bonding, dipole-dipole attraction, and London dispersion forces. Who remembers any of that? Then maybe the terms, just the terms. Okay, so basically stuff gets close together, they could potentially interact. Well, what do you think is going to happen if particle 1 and particle 2 are far apart, they have a big volume, but as they get close together, we expect they would stay this volume, but no. They interact, so what happens to their volume? It reduces, it gets even smaller than what we predict. So that's why we say this is more true at low pressures where stuff's far apart enough that they're not really going to interact. Okay, Charles's law. He went to Virginia Tech. So volume and temperature, and if you get it out your box of air again, okay, box of air, particles at whatever the temperature is, room temperature right now, they're bouncing off the container, they're kind of moving around. As you heat them up, what do the particles do? They what? No, so they don't necessarily spread out yet, but immediately you heat them up, what do they start to do? Move super fast, right? So in your box of air, you can drop it for a moment. In your box of air, the particles are hitting the sides of the container, right? At some speed. Well, when they hit the sides of the container, what is that causing within the container? Pressure. So you should know pressure is not just a unit we kind of reference. It's actually the number of collisions with a container. So pressure is a constant here. What else is a constant here? And amount, right? So moles. So if I have my container and it's bouncing at like 25 degrees C, and we've got a certain pressure, and then I heat them up, what happens to the number of collisions with the container walls? Okay, so they're really bouncing off the walls, and so they're basically going to increase the pressure. So then what do you have to do to make that pressure stop increasing? Increase the volume to give them more space, because if they have more space, are they as likely to hit the container wall? No. So it's not just by nature like, oh, if I increase the volume, temperature increases. It's actually the other way. If I increase the temperature, the volume should increase in order to keep the pressure constant. So if I increase the temperature, the volume should also increase to maintain a constant pressure. And so that's a direct proportion, or a direct relationship. So the equation for that is for like the scenario 1, scenario 2, V1 over T1 is equal to V2 over T2. Now, the way that this was initially explained, it was, space here. It was initially explained in Celsius, and V, volume, and temperature in Celsius had a direct correlation, so it had a positive linear line. But, and I actually graphed that a little wrong. Let me go back here. It doesn't go to 0. It's like this, kind of. But this point right here, where their volume is theoretically 0, is what temperature? It's absolute 0 Kelvin, which is what in Celsius? Negative 273.15 Celsius. That's the theoretical point where all volume collapses upon itself, or matter collapses upon itself, and nothing moves, period. But that's theoretically impossible, because your matter cannot collapse upon itself, because it still takes up space because it's matter. So we've actually never reached absolute 0, which this is that right there. So 0 Kelvin is absolute 0. One guy made it there. He's okay. Okay, guys, you guys stay with me. Okay. So no, we've never made it that far, but we've gotten very close, and they do see that particles stop moving so fast. I try to be as corny as possible. Okay. I'm just making sure I'm telling you everything I want to tell you. Yeah. Okay. So then now Avogadro defined the mole, right? So our variable, the mole, is N. So he related moles, which is the variable N, and anybody? It's okay. Just take a stab at it. Volume. Okay. All right. So take your box of air. Oh, sorry. Before you do that, what variables are constant if these are the only ones utilized? Pressure and temperature. Okay. Box of air, certain volume. Let's say there's 1 mole of gas in there. All right. Pump another mole of gas in there. Don't you expand yet. We're pumping another mole of gas in there. What's happening inside our container? Lots and lots and lots of collisions, right? Double the collisions. So what should be happening to pressure? It should be increasing, but no, you cannot. Pressure must stay constant. So what must you do? Increase it so there's lesser collisions in the container wall by nature of more surface or more area to travel. So they are directly proportional because as you increase the moles, the volume increase to accommodate for those moles. And that's a direct relationship. Okay, and with that, there's not much else to do there. Okay, so these are three, oh, I forgot the equation. So if it's directly proportional, we're going to write it similarly to whose other law? Charles's law, so we're going to write it as N1 over V1 is equal to N2 over V2. So in this one, what does N have to be in terms of units? It has to be described in moles, not grams, and volume can be in liters or milliliters. I didn't mention this one. What is volume, or what could volume be in? Liters or milliliters, and then what does temperature have to be in? Kelvin. You cannot use Celsius at all in gas laws. It's related to kinetic molecular theory, which you guys saw a little bit on your simulation. This is stuff from National Math and Science Initiative, NMSI. There's a study guide on my website. It's really good. I would use it for study evidence, but this just explains a little bit more about Boyle's law. No need for this. Moving on. And I think we mentioned this already. Here's your Kelvin, and you'll notice that everything essentially goes to zero volume there, which is absolute zero, theoretically, but there's that, this is a positive relationship still. We see differences, as you can see across the board here, in different types of molecules, and that's actually because of intermolecular forces. That's actually why. So hydrogen or helium doesn't really interact because it's a noble gas, so its volume stays quite large. But like water is a polar molecule, it undergoes hydrogen bonding with other waters or other things like itself, so its volume starts to condense faster, and so does this is polar as well. So there's some differences there based on mass and on interactions. All right, what's an ideal gas? Talk to the person next to you, see what you can remember. CJ, jump in the conversation. All right, come back to me. Come back to me. Cassie, tell me one thing that we describe an ideal gas to be. Okay, so we assume that it has a negligible volume, and that's because the gas particles themselves technically take up volume, right? Like they're matter, they take up volume. But if they take up volume, then we have to take volume total of our container, and we have to subtract the volume of the particles to get the actual volume in our problem. Ain't nobody got time for that, okay? So we do not do that because we assume they have negligible volume, which kind of gives us the convenience of just saying, hey, this is a 1 liter container, I'm working with 1 liter. Okay, what's another fact? Now,
All the collisions between the particles are elastic.
what's elastic mean?
Which is the energy's not lost.
Okay, so we're assuming that all energies remain the same because if they were lost, if energy was lost, what would happen to the pressure? It would fluctuate, but if the energy was lost, it would go down because they would be moving less fast, meaning slower, and then they would not collide with the container wall as frequently, so the pressure would be affected. Another fact. Do we assume that they interact with particles or don't interact with particles? We assume that they don't interact, meaning no IMFs, but really, we make that assumption just for our pure convenience, but we know that that's actually a fact they can. Is there another one? That's a pretty good list so far. We'll go to the KMT much later. But the idea is that we make all these assumptions so that we don't have to do hard math. That's really it. Scientists are like, let's make these assumptions so that we can have some predictability here without doing the hard math. So the equation that we'll be using for the ideal gas law is PV equals nRT with all variables denoted, and I'll explain this in a second, without having to subtract from the volume and subtract from the pressure and modify the relationships of interactions via IMS. So, my example in honors chem is always, is there really an ideal gas out there? No, there's only real gases. So, in terms of, I related this to, is there really an ideal man or woman out there for you guys? I'm sorry to crush your dreams. Is there? You have to compromise some. And just assume that they will meet your desired requirements. Okay, so if we're assuming that, this is the piece I'm really focused on here. If we're assuming that they don't interact, which we know they do, but if we're assuming they don't interact, at what conditions would they be so far apart that they truly, really wouldn't have a chance to interact? So what kind of pressure and what kind of temperature? Hold on, show me high pressure in your box. Squish, right? That's not going to work. They're really close together. So what condition for pressure? Low pressure would create ideal behavior with gas particles, and make a choice. So here we go. Low temperature. I'm moving slow. Oh, look. Hi, friend. Attract. Right? Unless I'm like moving really, really fast. I don't have time to interact with anybody. Right? So I'm zooming past each other. There's no interactions possible. So, tell me again. High temperature. Okay, so high temperature and low pressure allow for gases to act ideally, which is why we generally try to refer to that as much as we can. So when do the real characteristics come out? Low temperature and high pressure, basically the opposite of what we just had there, because that basically allows them to interact, and then we start to see the real characteristics come out. Okay, ideal gas law. This is a relationship which actually combines three gas laws we just learned. Who was the first one? Boyle's law, and then Charles's, and say again? Avogadro. So it combines pressure, volume and temperature, and moles and volume, which is how we get all the variables together to be P V equals nRT. The R is actually the universal gas law constant. And on your reference table, you get like 3 or 4 R values. I stick with one, and it's just because it creates a simplistic way of looking at it. So if I stick with one variable for R, that means I stick with one set of units for R. It's actually a gas law constant that brings in all the units from the pressure, the temperature, the moles, and the volume. Okay, so I use 0.0821 atmospheres times liters over moles times K for Kelvin. So it's a huge constant, and yes, you should be writing that unit every time. So if you have R in this unit, in this style, what should your pressure unit be? Atmospheres. What should your volume unit be? What should your M unit be? Moles. And what should your temperature be? Kelvin. If you look on the back of your reference table, does anybody have one nearby? It's K. But there's other ones with like with kilopascals, millimeters of mercury. There's some other ones you could technically use if you don't want to convert, but if we stay simple, you'll never get it wrong. Okay? All right, so we'll use that here shortly. Now, using the titles to this section, density from, density form, I was right. Density form of the ideal gas law. What is density's formula? D is equal to mass over volume, okay? And what is the ideal gas law? PV equals nRT. Okay, between those two equations, what is the one common variable? Volume, right? There's no mass over here. There's no density on this side. So volume is the V, is the same for both. So I'm going to rewrite this as D is equal to M over V. PV equals NR, or PV equals nRT. Rearrange both of those equations so V is what you're solving for. So V equals whatever here. Mass. So basically you move V up and D down. So mass over density. And V is equal to nRT over P. Okay. So since I have V isolated here and here, I technically could do what with these two equations? Set them equal to each other. So M over D is equal to nRT over P. So let's make some space. M over D is equal to nRT over P. All right, so we're still not done, but I'm showing you how to derive it if you ever forget it. Now I want you guys to solve the left side to be molar mass. What are the units of molar mass? Grams per mole. So what variables would that encompass? Mass and N, right? N. So I want this side over here to be mass over N. Tell me what the rest of it is. Rearrange the equation, algebra. So I pulled N down by dividing, so it's down here. DRT over P. Okay, so this is called the molar mass density, ideal gas law, but molar mass equation. I'm going to write that just a little differently, but it's the same thing. Molar mass is equal to dRT over P. Molar mass is equal to dRT over P. Okay, so they call this, who's they? I don't know, but they call this the molar mass kitty cat. It's because it's gross. It's because cats put their dirt over their pee. Like kitty litter, dirt over pee. Yeah, that's just saying, that's the way that people remember it. Okay, so molar, this is the one that I would be putting a like circle over around, because this is the one that we'll be utilizing more often than this one or this one. It's just how we derive it down. All right, so that's a new equation for us. But one note, and this is, I don't know if I put this on your paper, I'm not quite sure actually how in depth I put your notes, can't remember. But one thing about gases is because they take up so much volume, we don't denote their density as grams per milliliter because that's such a small quantity. We actually denote their densities as grams per liter because they obviously spread out and they expand, so their volume is quite large. So that's why density in this equation is in grams per liter. Okay? All right, moving on. Can I go? Awesome. All right, so this is like the last part of the introduction to notes, and then we're going to solve some problems. So a couple of you guys answered this part yesterday where you're taking the partial pressures. That's called Dalton's law, and I'm going to remember what my fill in the blanks were for. A mixture of gas is the same temperature. The partial pressures of each gas sums to the total pressure of all gases. So basically, partial pressure plus partial pressure plus partial pressure, however many gases you have, sums to be the total pressure. That kind of makes sense, right? Because pressure is a cumulative variable. So the equation for that one is P total, so PT, is equal to P1 plus P2 plus P3, and so on. If we only had two gases involved, it would just be two variables or two partial pressures. So assuming that all of these things are changing, what's going to be constant here? Volume, temperature, and amount, or moles. So all the other variables are constant. Okay, now this is a new one as well. I'm going to let you, do I have this on your paper? No, okay, take a minute and let's write. How about you guys write this down first and then we'll talk. If you can't see something, let me know. Some of the subscripts got kind of small. This is just like any other percent or fraction. You take part that you're interested in over total or over whole. So, for example, we'll be using mole fractions actually within partial pressure or Dalton's law with total pressure, because the X actually is the symbol for mole fraction, but when you put gas down there, you're actually identifying the gas of interest, so like hydrogen or nitrogen. So we'll take the moles of said gas and we'll divide it by the total moles of gas. So the abbreviation for that is X, which is mole fraction, is equivalent to moles of gas over total moles of gas. So that's actually going to be used in partial pressure or Dalton's law, because the partial pressures are proportional to the moles of gas they have. If I have a lot of moles of said gas, what should the partial pressure be? High. And if I have not so many moles of said gas, the partial pressure should be low. So it's proportional. So what we do is we try to relate this mole fraction to its partial pressure, PT, partial pressure. And so we can basically rearrange this to represent partial pressure instead, like down here. So X, meaning mole fraction, should be equivalent to partial pressure of the gas, which is the number of moles is proportional to its own partial pressure, and then total moles should control the total pressure. So we can just modify that as needed. So then, how can I rearrange this equation to solve for P total? Okay. Say again? Oh, hold on. Sorry, not solve for P gas. How can I rearrange this to solve for P gas? X of gas times P total. All right, so this is the one we will likely use in order to solve for the partial pressure of a gas if we have its mole fraction. So we'll solve for the partial pressure of a gas if we have its mole fraction. Okay, and then this is a kind of a behind the scenes, why can we do this? But no one really talks about the elephant in the room, like, hey, gases are different. They have different sizes. They can create different pressures. It's because if all of the gases are at the same temperature, their average velocity is what? The same. So the number of times they're hitting the container should be the same. So the identity doesn't matter. Because pressure is based on what? Say again, I heard somebody say it. Collisions, right. So identity doesn't matter because pressure is based on number of collisions, not necessarily anything else. There's more to it, but remember we make a lot of assumptions just to make our life easier. I wish we could do that all the time, right? All right, so I think I have a calculation on the next one. Ready? Almost there. Okay, so here you go. And I think I'm going to let you guys start without me first, okay? Read and go. Find the person next to you. I might just have to be doing this on another sheet of paper. I printed the bigger examples for you, not the smaller. While you guys are doing that, let me take attendance. Are you guys able to get started? Some of us are, okay. chlorine weighs 19 grams. Yes, okay. Just making sure. Okay, so as up here, if you're still working, just keep working. As you're looking at this and you're looking for partial pressure of each gas, given the total pressure, you have to find mole fraction first. Now, I didn't mention this earlier, but mole fraction does not have a unit because it's a fraction. Most time fractions don't have units, or percents don't have units. So once you get your moles of fluorine, and did ever use fluorine diatomic? Making sure, because your 7 diatomic molecules in their isolated state are diatomic, so you need to make sure that molar mass is doubled. So it gives you 0.5 moles, no calculator. Like, you could do this with no calculator, truly. And then your 4 grams of helium is truly just 1 mole of helium. So collectively, you have a total mole count of 1.5 moles. So 0.5 over 1.5 is 1/3. 1 over 1.5 is 2/3. So I just wrote it as decimal form, but you can keep it in your fraction form, no problem. What do you do next? Say again? You guys are so quiet. Multiply each partial, or each mole fraction by the total pressure. Guys, go get your question in a second. So for partial pressure of helium, we'll do 0.666 repeat times 4 atmospheres. You guys can do that in your head. If it helps, I'll do 2/3. Okay, so it's 2 times 4. 8, what's 8 divided by 3? 2.6. 2.666. Is that right? Yes. Okay. Alright, and then you guys do the other one. Okay. And what's the other one then? Oh, before you even do that, what's the other one that you could do without doing the mole fraction? Just subtract. So the total pressure is 4 minus 2.6 repeat. You get 1.3 repeat. Okay, so that should be the partial pressure of the other, fluorine. Alright, give me a thumbs up with that. Kind of after a second, you can put it together for yourself. Alright, stretch break. Get up, go talk to somebody. Get up and go talk to somebody. Hold on, let me go back. You can get up.
Last night I did with yeah. No, he's I ordered like you can order like yeah, but did your mom say like writing here like yeah, she did. Yeah, I did.
Everybody get some deep breaths and get some oxygen in your lungs.
Just in back of it.
Yeah.
Water in there.
Yeah, I did. I put like stuff in it, and then it's like over a bucket of water.
This one, given the fact we have multiple fractions. Okay. Okay. It's not. Right. So we do have to make that. But what happens is we say low pressure behind. Let me make that clear.
Or get back to your seats. You got like 5 seconds.
Because I added this one and this one.
All right, listen, I'm just going to repeat this out loud so we can hear, okay? Good question. When we were talking about the ideal gas law, or the ideal gases, we're talking about the behavior which we assume about them. We say we assume ideal behavior, or gases approach ideal behavior at those 2 conditions we mentioned. What were the 2 conditions?
So approach ideal gas behavior at high what? Temperatures and low pressure. Everything else we just assume, but it's closest to ideal at that point. All right, so here's another example problem. This one I think is on your sheet, right? Yeah, okay. So in this case, we're going to take 2 different containers, we're going to put them together. I'm sorry, 2 different containers with said gases. We're going to put those gases in another container. This is our empty container. I want to know what the partial pressures of each gas are given these variables. I'm not going to tell you how to do this. Try and then we'll go. Okay, try first. Problem solving efficiency. I would write down all my variables first as P's and T's and V's and see what gas laws slash in the face. One of them is going to come out. Go ahead, you brainstorm. I know. Got you. All right, you should have a gas law in mind and say it for me. 3, 2, 1. Ideal gas law, good.
Alright, so I know that you're thinking, okay, well, I've got two ends, right? Well, did we care about the identity of a gas? Okay, it's just about the collisions, right? So the pressure doesn't care about if I gotta do it twice. You could do two ideal gas laws and do that yourself. Or you could do what? Well, that's to get the partial pressures. I'm still getting total pressure. If I want to get total pressure, what could I do to the ends? Add them up, and that would be our total end for the total pressure. So I'm going for total pressure first, okay? And it's might be sloppy, but it's good. All right, so I have two end values. So when you sum those, that is in total to be 1.75. You guys got your T, added that to Celsius Kelvin. So that's 293 Kelvin. And you know, otherwise, you know one other thing from the problem. Volume to be 5 liters, and then from background knowledge, what should you also know? The R value, which is what? Atmospheres times liters over moles times K. Okay, so I'm going to erase this, I need space, but that's why I just explained pressure is collision space, so it doesn't matter about the identity, just add your moles together to get total moles, which give you total collisions. So P total is equal to nRT over V, 1.75 moles, 0.0821 atmospheres, liters per mole, K, 293 Kelvin, out of liters. All right, what's your total pressure? 8 point what? 8.4 atmospheres. Alright, so I know that you're going to hate writing these units all the time, but it saves you in the hand. My teacher made me always write them out and then cross them out to verify, which I think is a good practice. One second. To verify that everything cancels that you need to. So does moles cancel? Yes, moles here and moles in the denominator of the R. Does atmospheres cancel? No. This is why it stays with us. Does liters cancel? Yes, top and bottom of the bottom fraction, or bottom meaning fractions. Does Kelvin cancel? Yes, because it's on the top and then the bottom of the R value. So the only unit left is atmospheres. Question? Do not add the numerical. So this is one big honking unit, atmospheres, liters per mole K, and all of those units are described by this number. 0.80821 describes these units. Separately, you have your other variables though, where you put your numbers. Okay. So now let's how do I get partial pressure from the total pressure? So let's do mole fraction. This is a practice. So what's our mole fraction for hydrogen? 0.5 moles over what? 1.75 moles. Sorry, total. And what's our mole fraction for, what was the other one? Who was the gas? Helium. Okay, so we'll take our mole fractions, we'll multiply by the total pressure, and we'll get our partial pressures. Okay, so what is the partial pressure of hydrogen? So you're taking mole fraction times P total, and you got what? 2.1? 4. Okay, so that's our total, or that's our partial pressure for hydrogen. And then P of helium is equal to partial pressure, or mole fraction of helium times total pressure. Or you could just subtract from 8.4, so it should be 6 atmospheres. Yes, ma'am. Yeah. You would have your work there for that, and the idea is that you're probably just getting points for both partial pressures, not necessarily your process. If they ask for mole fraction though, then you'll have already had that one. Okay. All right, we have a couple more problems. Give me a thumbs up when you get here. Thanks for being troopers. Thanks for being troopers. Yeah, do this one. I think I'm not gonna do this next one, but do this one. Try it first. I like to let you try to think your problem solving process through first. The temperature's not changing, so no. Anybody want to confidently raise their hand and tell us the beginning of your problem solving? Or not confidently raise their hand? Either way? Okay, take another minute. I'm just like asking for the start, like the final answer. Gabby? Not yet. I guess don't be scared to make a mistake, man. Come on. Okay, so starting off, let's get the person saying yes. That's a good start. Okay, but what am I looking for at the end, Miriam? But those, to find the moles, and then go back and do ideal gas law? You could. I think that might take you as longer. Let me tell you my thoughts on what I know. I know that neon in this volume which is 2 liters. I know that its pressure is 420 torr. Separately, I want to find neons. This is all for neon. I want to find neon's pressure in a bigger volume once I open this valve and let it kind of go out and play. So what's that bigger volume I'm trying to find the pressure of? So 2 liters plus 0.5 liters is a V total of 2.5 liters. So I want to find neon's new pressure in a bigger volume. What gas law is that? Say again? Boils, right. So we got to do neon separate from helium. But I think that that's more approachable than trying to go to moles and use R values and go through ideal gas law. But hey, tomato, you can definitely do like 3 different ways. Yeah.
So the gases are like, the valve is like between the 2 gases?
Yes, this is a cutoff between the 2, and then when we open it, the valve allows for the gases to disperse across. So if I know V1 and P1, and I know V2 is 2.5 liters, because that's the total volume for neon's new landscape it can kind of travel about, I want to know P2 for neon. So all this comes together to be what law? Well, hold on, P1 times V1 equals P2 times V2, so I need to solve for which variable? V2, so V2 is equal to what rearranged equation? P1 times V1 over P2, so you guys can do algebra and rearrange. And as we go here, P1 is, oh, I didn't mean to solve for V2, sorry. I have to solve for P2. Just did it again. Ooh, all right. I'm solving for P2. Okay. So P1 is 420. Okay, I was trying to mention math. 1680 divided by 5. I'm not sure what this is. What is this in torr? Loud and proud. I'm done up here.
333.
336. Thank you. Somebody's got me here. All right, so that's our partial pressure of neon in the bigger container. So what do I need to do for helium? The same thing, but you have a different starting point in pressure and in volume. So that was for neon. What is this? Two what? What does it say in atmospheres first? 0.3? Yeah. So this is 0.3 atmospheres, which is P2. And then, Megan, what is that in torr? 228. So you divide it by 760, right? Or multiply by 760. 228 torr. So that's partial pressure of helium. So then collectively, when you add them together, what is it? 564 torr. P total. Probably. Sometimes I'm bad about that. So 560. Yeah. Yeah, there was not a designated variable here. So 560 torr, which is how many atmospheres, Darcy? How many atmospheres is that? 0.74. So both of those are 2 sig fig. So those plus probably many other answers would be acceptable. Okay, we have one more thing, but I don't know if we're going to be able to get there right now because you guys are probably a little bit dead that thinks we're working with me. Let me look and verify this. Give me a thumbs up when you're good here. There's really only one more thing. We can push, right? Push through? Okay. No, we won't do that one. Here it is. Okay, is this on your paper? This is not on your paper? Okay, so I'm going to talk you through this. This is for our experiment on Friday. But I want to talk you through what we were going to do with this. So I'll break out the pieces of this right now. After I'll talk you through it. I think it's only 5 minutes. If you want to take a picture of it, that's fine. I'm videoing. This is more for application base. So basically, we don't have mercury, right? We're not hooligans. We don't have mercury in the chemistry classroom. I do have one mercury thermometer. I need to find a way to get rid of it. No, not all, I'm not chemistry. So basically, since we can't use mercury, we use water for our barometers or our pressure measurement detectors. So since we have to use water, we have to find the relationship between water and mercury. So we spoke of this earlier. Mercury has a density that's really dense, 13.6 grams per milliliter. Water's generic density is what? 1 milliliter, or 1 gram per milliliter. So what we'll do is we'll set up a container with a little beaker with water, not mercury in it. We'll set up this eudiometer tube, which is an upside down big huge test tube with little lines on it, but they're not in millimeters, they're in milliliters, because that's what our measuring devices in volume will do. Now, what we will do is we'll react something in our eudiometer tube, and the reaction will happen up here, and it's making a gas. So gases float, right? So the gas bubbles will be all up here, but all this other stuff will be full of water, because our water is where we're basically doing water displacement, but it's upside down. So the water is being evacuated down into our beakers, but the gas is rising to the top. So the water level's up to here. So, I have to find a way to convert milliliters of water or height of water to height of mercury. And that's where I can then incorporate the water displacement into the total pressure overall. So, if I want to know the pressure of that gas that's at the top of my little Uviometer tube, I first need to know the total pressure, and I will subtract the water vapor pressure because, you know, this is water. Water really quite easily vaporizes, right? So the vapors of water will be up here in the gas. So if I just isolate the stuff on the top, I actually am going to have gas that I care about and then the water vapor as well, and I can't have both because I don't care about the water vapor at all. I care about just the pressure of the gas. So I must subtract the water vapor pressure from the total pressure overall. This is going to be in a book. Inlet will tell you the vapor pressure, and it'll be at a specific temperature. So if this is 20 degrees centigrade, then you'll have a certain pressure, and if it's 40, you'll have a different pressure. So we can't just memorize it as from a book. I'll show you how to do that later. We also have to subtract the pressure that this water column is causing, and here's how you do that. So the water vapors from a book, water column is done this way. So water column is this height right here, right? See H2O? We want to convert that to H of mercury because that's the pressure unit, millimeters of mercury, that I can actually utilize in pressure situations. So I'm going to take the water height, like I can use a ruler and actually literally measure it in millimeters of water. I'm going to multiply that by the density of water, which we generally regard as what? 1 gram per milliliter. And then as I took this equation, I rearranged it and did what? Solve for H mercury, so I divided by mercury's density. So I'm going to divide by 13.6 grams per milliliter. What cancels? Grams and milliliters, so I got millimeters of water, which I've effectively converted to millimeters of mercury. And then I can utilize millimeters of mercury in my pressure, Dalton's law, partial pressure stuff equation. Right, we will eventually do this in the lab, but the idea is that we understand it's just Dalton's law. Okay, pull out your packet. Let me tell you where you're going from here. We leave in a minute. I'm going to look at some of these packets for a minute. Look at the heavy things. Look under where it says optional. It says gas laws, problem set, express all final answers, right, safe fix. It says optional on it. I have stars on 4, 5, 7, and 8, 7, 8, and 10. So I have stars on 5 of them. Do you see that? It's in the back of the lecture sheet. Back of the notes from today. Those are the ones I definitely want done. The other ones are there for you, but I think if you need to practice your gases, then those would be good ones to go about. Sorry, I don't see answers on the bottom, but I will go over answers tomorrow with you. And then I was going to sign this yesterday, but I switched it to today because you guys can finish your simulation. There's a couple of really good textbook problems. The odd ones, the answers in the back of the book. So if you can't do an odd one, try to, or if you can't do an even one, try the odd ones first, and that's probably the even ones. So you have 5 problems from problem set, and then a couple of questions from textbook. Okay? Guys, have up. That was yesterday. Yeah, I checked it. So yours is on your desk yesterday. Right? I checked it yesterday. Oh, I checked the first half of it. I'll check the rest of it later. Bye, guys. Yes. Whenever I teach you get these online. Guys, I'll look at active reading guides tomorrow. I got started fast and didn't check it. I'll look at it tomorrow.